Okay, thank you so much. It's a pleasure to be here, and I'm Mark Elless. I'm a technology manager in the Bioenergy Technologies office, and I would just like to present today an overview of our DOE's concept on the advanced feedstock supply systems enabling affordable access to distributed biomass resources. Before I begin, I would just like to describe or present what the Bioenergy Technologies Office does. Our mission is to develop and demonstrate transformative and revolutionary sustainable bioenergy technologies for a prosperous nation. And we do that by conducting and supporting research, development, and demonstration activities along the supply chain. The first, of course, it starts with feedstocks, and that's where I work. And that is, my colleagues and I, we work to develop cost-effective systems for bringing biomass to conversion. And we're looking at both terrestrial and algae feedstocks. Once we hand it off to the conversion people, then they support R&D to convert the biomass into bioenergy, whether that's biofuels, bioproducts, or biopower. And they do that through a combination, either biochemical or thermochemical methods. And lastly, the demonstration of market transformation platform area focuses on to demonstrate and validate technologies to, again, convert feedstock into bioenergy by supporting both the pilot and demonstration scale facilities. And cross-cutting through all of those three platform areas is we have sustainability, which underlies a lot of our thinking in Beetle. We certainly want to have sustainable feedstocks and using processes that are sustainable to convert the feedstocks into bioenergy. Then we also have strategic analysis, which helps guide our thinking, making sure that the next area that we support is worthy of federal funding, and the strategic communications, which is our outreach and just getting the word out of what we do. So now I just want to turn my attention. I'm going to compare what's happening today with what DOE's version or vision in the future. Today, a lot of the biorefineries are being fed by a conventional feedstock supply system. And this is a vertically integrated system. And it works for either herbaceous or woody biomass. But basically, the biorefinery has perhaps like a 50-mile supply radius surrounding it, and it collects all that biomass and it feeds that one biorefinery. And it's pretty much one feedstock going to one biorefinery. The location of the biorefinery is key for this system to work. It wants to be in a very high-yielding niche area so that within the 50-mile radius, it has more than ample supply to keep it going. However, there are problems that could come up. You know, if there's a supply disruption within that 50-mile radius, drought, flooding, pests, then the only avenue that the biorefinery has to access more biomass is to expand that radius. And then it gets very costly if they have to transport farther from the biorefinery. But other problems with the conventional system is it's just taking whatever the biomass is directly from the farmer's field and delivering it to the biorefinery. There's not a lot of active quality management. And so you can have inconsistent quality in terms of the moisture of the biomass coming in. We heard a lot from the previous panel about the ash content, you know, that could be too high. In terms of moisture, you could have high dry matter loss if the moisture content's too high and it's stored too long. It's a low bulk density, so there's problems with flowability. It's not like in the grain industry where it's more like a pellet that's being moved. And so all these problems have led to lengthy startup periods and low throughput on pioneer biorefineries. Now, on the other hand, is the advanced feedstock supply system. And what we feel which is the hallmark of the advanced feedstock supply system, is now we are wanting to have that biorefinery decoupled from the supply area. So now you have a network of distributed depots surrounding or within the region of the biorefinery, and they're the ones that are collecting the biomass. And they can collect even more than one feedstock type. They can get access to what would have been called stranded resources or biomass that the conventional system would have left in place because it wasn't economical for them to get their hands on. But now you can also maybe acquire, in terms of different feedstocks, waste, maybe MSW or C&D waste, but waste that are perhaps less costly, that when you actually process within a depot facility, you can bring in low-cost feedstocks to help make the blend lower cost, and also through blending also to do a bit of active quality management and being able to bring down the ash content, have dryers in the depots as well, bring down the moisture content, and try to provide the feedstock that actually meets the conversion specs the in-feed specs that the conversion facility needs. So we spoke about the enhanced quality, again, the reduced supply risk because it's decoupled from the biorefinery. It basically increases the supply radius and gets access to much more volume of biomass. Other things that could occur in the depot is also densification. You can, instead of relying on having a low dense biomass that the conventional system supplies that's not flowable, you can densify, make them into pellets, and it certainly conveys more through the biorefinery. This schematic by Idaho National Lab just shows one type of supply disruption and how the conventional system handles it versus what the advanced feedstock supply system could. And in the I guess to your right, the year A scenario, it shows, now this is for a drought. It shows that the regions affected by the drought are actually outside the areas of both the smaller yellow dotted circle for the conventional supply radius or even the expanded depot circle. So in that year, probably the conventional system's not a bad system. They could probably even provide it biomass to the biorefinery at a lower cost. But again, the quality may not be as well. However, if you look at year B, and now within that conventional system, you have drought conditions that are affecting supply. Again, the only avenue left for the biorefinery to access more biomass is to expand that's radius, and it adds a lot of cost. And INL has provided some numbers that it could go up as high as 60% greater just by expanding that radius. Even though on that, I guess on your left, you can see that the drought conditions affect some depots. If you actually do have a distributed network of depots that are supplying a biorefinery, some may be affected, but others are not. And so you really mitigate that risk of supply by having a network of depots set up. And this is just one example. This is only for drought, but again, you could have flooding, you could have pests. So the more potential disruptions in supply, I think you can see the value of the advanced feedstock supply system. And especially if there's a weather event that is impacting the harvest window, which is pretty short, and I think John will talk about that. If you get a lot of rain coming at the wrong time, then that's also going to impact how much could actually be harvested and sent to the biorefinery. This graph illustrates that, especially what the other panel had said before, certainly the more that you pre-process, the more that you touch, the cost for that biomass does increase. And so this graph is certainly showing that for the conventional system, up until a certain point, it will be the low cost option. But eventually, if you keep on building biorefineries and they're doing conventional supply systems, you're going to run out of places which are really high yielding. And to get to that next ton is going to start getting more and more expensive. And you're going to get to a crossover point whereby advanced systems then become more cost competitive, and in fact, even cheaper. The shading on this graph is just showing that if for some reason, because of all that pre-processing advantage and by improving quality so that that you actually meet the in-feed specs, and by doing so that you can actually improve the conversion efficiency, maybe you have a lot of downstream benefits that you can reap and try to recoup some of that cost that makes advanced systems more costly to begin with. And so certainly if you're able to bring or actually identify those downstream benefits and quantify them, and you can close that gap. And then the advanced systems, and what we're looking for in BITO is try to close that gap so that no matter what volume, that advanced systems will be the preferred option. And also, as you see, conventional systems really get you to, I mean, it becomes asymptotic at a certain volume. And if you read the latest billion-ton report, they're putting that at about 140 million dry tons. Now that's a lot. We're only probably doing 1 or 2 million right now. But it doesn't get us, if we want to really meet the RFS2 target, we need 285 million dry tons. And so as you can see, the advanced systems, because it's able to access more biomass, more of the stranded resources, more of the waste resources, you can probably more easily achieve the volumes needed to meet RFS2. This just reiterates, I think, a few points that the earlier panel also brought up. But these are just some of the near-term strategies for transitioning from a conventional system to an advanced. And I think the first thing that we need when we're looking at a transition is we got to decouple the biorefinery from the supply circle. We got to be able to institute a network of depots. And that's really going to increase, again, the supply certainty to the biorefinery. Next in line, and I think what Tim was talking about, we got to make sure we have those inline sensors so that we can monitor moisture and ash. I prefer using ash rather than dirt because I'm a soil scientist. I don't want to be called a dirt scientist, but I stole this from somebody else who wasn't a soil scientist. But anyway, but let's just keep, if we monitor the moisture content and the ash, which are two of the biggest problems that the conversion facilities are experiencing because of in-feeding problems, if it's too wet or the ash is too high and there's, it's wear and tear on their equipment, then let's monitor that throughout. And then if you identify that they're too high, try to reduce the ash content even before it gets to the refinery, maybe by harvesting techniques like one pass harvesting, or even if there's ash that gets to the or to the depot, say, being able to use pre-processing techniques within the depot to reduce that ash, whether that's air classification or washing, whatever. And then certainly the densifying the feedstock could certainly occur within the depot system. And again, there's a lot of benefits for that. You increase the energy density of the feedstock, and you can transport that feedstock a lot farther and feed different biorefineries if you actually do densify. And just in summary, I just want to show what we consider the three aspects that really highlight the value of the advanced feedstock supply system. Again, we believe we're adding value to the biomass. We're transforming that biomass into a feedstock that has uniform characteristics that meet the in-feed specifications. We believe we're mitigating the risk, again, by decoupling the biorefinery from the supply and having the depots take more of that risk. But because there's a network of depots, they're being able to access more biomass, and the actual supply to the biorefinery is not threatened. And finally, to develop feedstocks into a commodity, a tradable, aggregatable commodity that could then open up markets and companion markets, which will also, as early in the supply chain, to help lower the cost of the advanced feedstock supply system. And that's all I have. Thank you.